Welcome, math friends. We are going to be talking about polynomial equations today. Remember that with polynomials, you are dealing with powers that are positive or zero. You're not going to have any negative exponents. Your highest degree is the highest exponent number. We have leading coefficients. You are probably familiar with constant functions. That's a number without a variable. You have quadratic functions, linear functions, cubic functions, quartic functions, and so on. Maybe you have something to the 12th power. That would be a degree of 12. Polynomials are strung together with addition or subtraction symbols. If you've watched the quadratic equations video, you know that there's 5 different ways that we have solved those quadratics. You can use the zero product property with factoring. You can use the principle of square roots. You can use completing the square. You can use graphing, and you can use the quadratic formula. The way that you're going to solve polynomials depends on the way that the equation presents itself. If you have something that is quadratic or linear, you would reference the quadratic equation or linear equations video. But when you get into higher powers, there's a couple of different strategies that would use. You would want to use the rational zeros theorem to help you and then break it down even further. Let's talk about the rational zero theorem first. The rational zeros theorem uses the divisors of the leading coefficient as well as the constant term, all of those factors combined together, and then whatever value makes that function zero is a factor. So if you take p over q, let's say, for instance, you have this x to the fourth minus 5x squared minus 36 equals 0 problem that we're approaching. The leading coefficient is 1. So the dividers of 1 is just 1, but it could be positive and negative. The divisors of 36, you've got 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6, and positives and negatives of all of those. So you work with all of these different combinations to find a P over Q that when you plug it into the equation gives you a 0. And once you do that, you have a factor, and you can then divide out that factor, reduce down your polynomial, and then continue to solve that way. So you could use synthetic division is probably my favorite versus polynomial division to help you once you get a factor to reduce down your polynomial. When you have a polynomial, remember that imaginary solutions come in pairs. And so it's important to know that if you have the square root of 3i, you would also have the negative square root of 3i. They come in pairs. Your highest power will tell you how many real answers you will have at most. So if you have something to the 4th power, you will have at most 4 real solutions. You could have 4 real solutions, 2 real solutions, or no real solutions, depending on if you have imaginary components. So let's start off by solving this first problem by listing the factors that we have of our leading term and our constant term. Because our Q is plus or minus 1, essentially every single term that is a divisor of the constant divided by 1 is just itself. So I don't really have much to write over Q. So the P values are also going to be our P over Q values. That is plus or minus 36, plus or minus 18, plus or minus 12, plus or minus 9, plus or minus 6, plus or minus 4, plus or minus 3, plus or minus 2, and plus or minus 1. Those are a lot of divisors. So there's a lot of different numbers that I could plug in to find a 0. Let's use a little math sense to help us find a reasonable value. I'm going to be taking one of these divisors, or one of these P over Q terms, and I need to plug it into the 4th power minus 5x squared minus 36. If I take 36 to the 4th power minus 36 squared, that's going to give me a very large number. So I don't really want to start with my 36 and my 18s and my 12s. I want to start with something smaller. Now, 2 to the 4th power is only 16. So I want to go maybe a little bit higher, but 3 to the 4th power is 81. So let's just try 3 really quickly. So what I'm going to do is I'm going to plug in 3. Now, Positive 3 and negative 3 are going to give me the same number because they're both, all of the powers are even. So negative 3 to an even power is going to become positive, and positive 3 to a power is going to become positive. So any number that I find, its opposite sign is also going to be a solution. But let's start with 3. 3 to the fourth minus 5 times 3 squared minus 36 equals 0. 3 to the fourth is 81. Minus 5, 3 squared is 9, minus 36 equals 0. That's 81 minus 45 minus 36 equals 0, which is 0. Because 45 and 36 is 81, and 81 minus 81 is 0. That means that 3 is a solution. Negative 3 is also a solution, but we can come to that later. So what I know is that 3 is a 0. When I have x equals 3, the way that I write that as a factor would be x minus 3. So if I was to try and factor this, I know that x minus 3 is one factor, and I want to figure out what the rest of the factors are to help me solve. I know that x equals 3 is an answer, but also if I'm writing as a factor, that's x minus 3. So let's use synthetic division to go ahead and reduce down by factoring out the x minus 3. The way that I do that is I write each of the pieces out, the coefficients, when I'm doing synthetic division rather than polynomial division. So my leading term is 1. I have no third power. That means its coefficient is 0. I have negative 5. I have no linear term. That means the coefficient for that is 0. And then I have negative 36. And I'm dealing with 3. I put the actual equal to value on the outside. I'm going to drop down my 1 and then multiply. 3 times 1 is 3. And then I'm going to add those two together to get 3. And then I do that again. 3 times 3 is 9. 9 plus negative 5 is 4. Now, because 3 is a factor, this is going to give me 0 as my final term, but I'm reducing down to the third power. So I'll show you what happens. 3 times 4 is 12. 12 plus 0 is 12. And 3 times 12 is 36. Negative 36 plus 36 is 0. What I've done now is I've reduced to a third power, second power, first power, and constant term. So I can rewrite the part that's left over when I factored out x minus 3 to be x cubed plus 3x squared plus 4x plus 12. That's what I have so far, and that's equal to 0. Now I can approach this quadrinomial and attempt to work with it. Now looking at this, I could then do the rational zeros theorem again, working with 12 and 1 and plugging that in to get 0. But what I'm actually going to do is recognize that I can factor by grouping here. And factoring by grouping is easier than having to list all these factors out and write it down. So when I factor by grouping, I factor out what's common to the first two terms and the last two terms. And this only works if you have something that's common that leaves you with nice components. And then I can factor that. So x cubed plus 3x squared, I'm going to factor out x squared. That leaves me with x plus 3. Now, in order for this to work, I need to be left with x plus 3 when I factor out something from 4x and 12. 4x and 12 factor by 4. That leaves me with x plus 3, which is good. That's what I needed for grouping. I still have this x minus 3 term here. And then I can factor out this x squared plus 4, which means I have x minus 3 times x plus 3 times x squared plus 4, and that's all equal to 0. Now I can use the zero product property to solve, setting each of these components equal to 0 to get my answers. X minus 3 equals to 0 gives me a solution of 3. X plus 3 equal to 0 gives me a solution of negative 3. And x squared plus 4 equal to 0 gives me an imaginary number pair. That's going to be x squared equals negative 4, or x equals plus or minus 2i. When I square root 4, I get 2, and the square root of a negative 1 is I. That remember that the imaginary numbers come in pairs. So my solutions are 3, -3, and plus or minus 2i. But when we say solve for x, we're looking for the real solutions. Unless the question asks you to list the imaginary solutions and the real solutions, you would not want to, you would just want to say x equals 3 and -3. Moving to the next question, I have x cubed minus 1 equals 0. I can go ahead and use the principles of square roots here because I have x cubed, there's no other x's anywhere. I can add 1 to both sides and say x cubed equals 1, and then I can cube root both sides to undo the cube. X cubed cube rooted is x, and the cube root of 1 is 1. It's not plus or minus 1 because it's to the third power, and something to an odd power retains its sign. -1 to the third would be -1. Cube root of -1 would be -1. So it's important that you're paying attention to whether you have an even or an odd power. Moving on to my next problem, I have 4 terms together, which typically I can, whenever I have 4 terms together, I want to factor by grouping. If you can't factor by grouping, then you need to use the rational zeros theorem to find a factor and then divide out like we did in the first problem. Looking at this, they both have x's, they both have 3's. I'm looking pretty good for grouping here. The first 2 terms share x squared. That leaves me with x plus 3. And x and 3 don't really share anything, so I could take out a plus 1, but that leaves me with -x minus 3. So if you look at that, those are not the same. They have the same variable and the same number, but the signs are not the same. And that's an indication that I need to take out a -1 as my factor. And that leaves me with x plus 3. Then I have x squared minus 1 and x plus 3 equals 0. Now, that is a sum and difference. I could split that up to x plus 1, x minus 1. I'm going to get the same answers if I don't. I can now use the zero product property to set each of those equal to 0 and solve. That's x squared equals 1 and x equals -3. Square rooting, I get x equals plus or minus 1 because 1 squared is 1 and -1 squared is 1. That means that my solutions are -1, +1, and -3. This was a polynomial to the third power, and I have 3 real zeros here. In my last problem here, I have x to the 4th plus 3x squared minus 18. For this problem, I can approach it the same way that I approached the first problem. However, I want to give you a different strategy, which is actually a strategy you could have used on the first problem. These are to the 4th power and to the 2nd power. Those are even powers, and I can approach this like I would a quadratic. And instead of having x and x factors, I'm going to have x squared and x squared factors. So I'm going to see if I can factor this first. I can't factor it using grouping because there's only 3 terms. But what multiplies to -18 that adds to 3? 1 and 18 don't work. 2 and 9 don't work, but 3 and 6 do. If I take a +6 and a -3, that's going to work out for me in terms of splitting this up. That's x to the 4th plus 6x squared minus 3x squared minus 18 equals 0. So what I've done is I've taken this middle term and I've split it in 2 because I'm looking for a product that gives me -18 and a sum that gives me +3. And 6 times -3 is -18, and 6 plus -3 is 3. Now I can factor this by grouping. Taking out an x squared, I have x squared plus 6, and taking out a -3 gives me x squared plus 6. I then have x squared minus 3 times x squared plus 6 equals 0. And I can set each of those equal to 0 and solve. That means I have x squared equals 3 and x squared equals -6. I'm going to have real roots and non-real roots. Square rooting both sides gives me x equals plus or minus √3 and x equals plus or minus √6i. So my actual real solutions are plus or minus root 3. I hope these strategies helped you and gave you some confidence in solving polynomial equations. Thank you for watching. Have a great day.